Okay, let us start our afternoon session. Our only speaker without Chinese affiliation, Mikhail Vasilev from the University of Glasgow.
Okay, thank you. First, I'd like to thank all the organizers for giving me to give this talk. It's also my first ever trip to China. It's really nice here. So I'll talk about our work in progress joined with Misha Feigin, Korff and Martin Vrabec, all from the University of Glasgow. So I'll speak about different systems, which are called generalized spin Calogero-Moser systems. I will derive them from representation theory of rational Cherednik algebras, well, from Cherednik algebras too, but I'll focus on rational case just for simplicity. So the plan of the talk is the following one. So firstly, I'll give a small reminder about a very classical story about how Calogero-Moser systems could be obtained from Dunkl operators. Then I'll talk about just generalized Calogero-Moser systems without spin and how they could be obtained from reducible representations of rational Cherednik algebra. Then I'll talk about our results about generalized spin Calogero-Moser systems, which will be obtained again from reducible representations of Cherednik algebras. Then I'll do some interesting examples, and then I'll speak about possible questions which could be asked about this work. So firstly, I need to define what is a rational Cherednik algebra. So rational Cherednik algebra is, so firstly, we can define it through generators and relations. So we have three types of generators here. So we have W, which are from Weyl group, X's are from dual Cartan, and nablas are from Cartan. So I fix some root system R. I have Weyl group, and I have Cartan and dual Cartan. So, and I need a little bit more additional information. So I have a multiplicity function C from root system to complex numbers, and I want only one thing from it. I want it to be Weyl-invariant. So it is constant on the roots of the same length. So then I just say that W, they generate Weyl group. Then X's, all X's commute and all nablas commute. And then X's and nablas are equivariant with respect to Weyl group action. And then I have a relation between nablas and X's. Well, a little bit more complicated, but still. So, but that's one way how we can define it. The other way how we can define it in an explicit way.
Sorry, maybe you said already, it's the finite root system.
Yes, yeah. yes. Nothing is affine. Oh, yeah, good. Thank you. Yeah, so an alternative way how we can define it through a faithful polynomial representation. So I define it through action on the space of polynomials. So I just say that X's, I define the action on the space of polynomials of X. And I say that X's will act by multiplication. W's will just permute X's. And then nablas will act by the so-called Dunkl operators. So they have divided difference operators, which we have seen previously in this workshop. And we have derivatives along sides. So this is a faithful representation. We can always think about rational Cherednik algebra just as algebra acting on the space of polynomials of X, and that's it. It's good enough. So how to obtain a Calogero-Moser system from rational Cherednik algebra and Dunkl operators? So what we can say, so we take polynomial representation, and I want to consider Weyl-invariant polynomials of Dunkl operators. So, and I want to say just the following thing. So Weyl-invariant polynomials of Dunkl operators, they are particularly good because they do preserve Weyl-invariant polynomials in X. So, and then I can try to compute what does it mean to act by a double invariant polynomial in numbers on invariant polynomials in X.
So will it be center of spherical RCA?
Yeah. So the simplest Hamiltonian comes from the second order operator. It always exists for systems. So I take psi i's to be my orthonormal basis. I square them. I sum all them up, and I take res, which is not residue, it's restriction. I restrict my action to symmetric polynomials in X. And I just compute explicitly the result. So you see that numbers, they contained s's, which were permuting x's. But since I act on double invariant polynomials in X, all of them disappeared. And I'm left with just some simple operator, which is written using just the information about my root system and multiplicity functions. And that's it. And we can go to the potential gauge. So, which means that I just conjugate my operator using van der Monde type function to obtain somewhat more physically meaningful operator with potential. So, and we see that the potential is somewhat kind of inverse of x squared. So, and this system is very well known to be integrable. We can take higher order invariant polynomials in numbers. We'll have exactly the number that we need for integrability. Everything here is very well understood. So that's a very classical story. Next question is how to obtain spin Calogero-Moser system. So what do I mean by spin? I mean the following thing. So previously I had just a scalar differential operator of second order. Now I want somehow to deform it so that it will act on some vectors. So what do I mean by this? So I mean the following thing. So instead of taking just polynomial representation, I tensor it with a Weyl group module, V. It could be any Weyl group module. And I will denote the action of the Weyl group on this module by P alpha. I will denote it this way because these are different from S alphas. So P alphas act on vector, while S alphas, they permute coordinate axes. So, and I just say a very simple thing. I want my whole rational Cherednik algebra to act trivially on V. So from the point of view of rational Cherednik algebra, nothing changes. I just tensor with something absolutely trivial. But still, it's a Weyl group module. And now I want to restrict the action of double invariant polynomials in numbers in my Dunkl operators, not to just invariants and not to just invariant polynomials. Now I have polynomial representation C of x, and I have invariant polynomials. Now, and then I tensored it with Weyl group module. And I have action of s's on C of x, which permute x's. And I have another action on V by my Weyl group by P alpha. And I take invariance with respect to the diagonal action. And now this will change the resulting operator. And I denote the restrictions to the space of diagonal invariance by res tilde. And again, there is a misprint, so it should be not partial derivative squared, but not the squared. So I compute the squares, I make a restriction, and I get another summand, which was not present in the previous formula. And you can see that it is proportional to 1 minus P alpha. And to get scalar Calogero-Moser operator back, I just need to say that all P alphas act by identity. And that's it. So this is a very simple story about how we can obtain spin Calogero-Moser systems from Dunkl operator. Now I want to go further. I want to study what is called generalized or deformed Calogero-Moser systems. So generalized Calogero-Moser systems, they are written with the help not of some set of vectors which do not form root systems. So here's the example for, well, somewhat type A system. So we have two types of particles, x's and y's. And in the denominators, you can see something that looks a little bit similar to type A root system, but it's weird. So we have xi minus xj, which is, well, quite usual. We have yi minus yj. Again, that's fine. But then we have yj minus xi over square root of k. So it's deformed by the number k. And if we set, yes.
Is that BCN an example of that?
Yes, yes, yes.
What happens if you rewrite it?
Sorry, but divided different these operators not preserved polynomials.
To preserve
Uh,
some kind of polynomial.
yeah, so the polynomials on which you need to act by these operators are quite weird. They're somewhat similar to supersymmetric functions that should be symmetric in x's and in y's, and there should be, well, a little bit weird relation between derivatives with respect to x and derivatives with respect to y. Then it would act on these polynomials. So it's a deformed story. And a strange fact is that, well, I don't have a formula in the potential gauge, but if we rewrite this in the potential gauge, the coupling constants will be different. So in one place we'll have some kind of k squared, in the other place we'll have 1 over k. So it's weird because the root system data is deformed by k. And we also need to take care of coupling constants. They cannot be different. They should be connected in this way. Otherwise, we'll not have an integrable system.
So where does k then?
K can be any number. For me, it will be a natural number.
Natural.
Yes. Yeah, so in principle, as far as I understand, the system will be integrable for, for every real, but from rational Cherednik algebra, we can obtain systems with natural k.
So if I understand you correctly, if you scale x by square root of k, you just obtain usual model with some masses.
Yes, with different mass. Yes.
Okay.
Because for integer k, you have polynomial representations, and if it's complex, you have it's still integral, but it's representation. I mean, there's certain, you can start with a complex k.
Yes.
Representation here, and see k is not integer.
Mhm.
You have translation.
Yes. That's what would happen. Yeah. So the idea how to obtain this system from rational Cherednik algebra from Dunkl operators is the following one. So let's try to study reducible polynomial representations of rational Cherednik algebra, and we can ask a simple question: when does a polynomial representation of rational Cherednik algebra, when is it reducible? So to do this, we need to introduce what's called invariant parabolic ideals, which goes back to, I don't know, something 40 years ago, maybe. Sorry, this story goes back to study of just reducible representation. So I will need the following data. So I take a root system R, a normal root system, finite root system. Then it has a while group. Then I draw a Dunkl diagram gamma, and I take a subgraph gamma node inside my Dunkl diagram. I denote by gamma v naught set of roots corresponding to my subgraph, and I have a usual multiplicity function, which is Weyl-invariant. And I want to assign to this data a submodule in the polynomial representation of rational Cherednik algebra. Of course, this will not always happen. I need to do some assumptions. I will have some restriction on multiplicity function and on gamma node. So, and the result is the following one, which is due to Misha Feigin. So what do we do? So we take a subgraph gamma naught, we take all the roots corresponding to this subgraph, and we take a plane orthogonal to all these roots. So, and we want to build something which we want to build a submodule of rational Cherednik algebra. We want this submodule, so it should be invariant under the whole action of rational Cherednik algebra. So firstly, it must be invariant with respect to Weyl group. So I can't just take just a plane. I need to take the orbit with respect to action of Weyl group. And so I take d gamma naught. I take the union of all planes obtained from pi by the action of Weyl group. So it would be some collection of planes with intersections, something like this. And then I define my ideal to be all the polynomials vanishing on this d gamma naught. Then a theorem due to Misha Feigin that e gamma naught, which we'll call invariant parabolic ideal, is invariant under the action of all rational Cherednik algebra, if and only if for every connected component of my Dunkl subgraph, the following relation holds. So, it's just some relation. I don't think that I need to go into detail. So we have a left-hand side and the right-hand side. They should be equal. So that's some restriction on gamma naught and C alphas. So it has quite a simple meaning in the case when the multiplicity function is constant on all the root systems. Then this relation is equivalent to multiplicity function being 1 over Coxeter number for all connected parts of the Dunkl diagram. For all connected parts of my subgraph. And for non-constant multiplicity function, it will be more complicated relation. So using this relation, we can try to search for invariant parabolic ideals for different root systems. So, and the construction of generalized Calogero-Moser system, a scalar one, not a spin one, is the following. So we take an invariant parabolic ideal, which we assume exists. So, and then we know that a factor module is again a rational Cherednik algebra module. And how we can think about this factor module? Well, it should be thought as a space of functions on my union of planes. So now I want to act not on the space of just polynomials. I want to act on the space of functions on the union of my planes. So here goes some technicalities. So the main idea is the following one. So now I want to write explicitly a differential operator, and and to do it, I need to do some computation in local coordinate. But well, my space is the union of planes, so I need to take local coordinates, and I need to be a little bit careful, but then I can still calculate the result, and the resulting operator looks almost like usual Calogero-Moser system, but with alpha hats. By alpha hats, I mean a projection of alpha onto pi. So I had my initial plane pi, I had my root, I had all the roots, and I project them onto pi. And that's my operator. And delta is the usual Laplacian on pi. That's the way how to think scalar Calogero-Moser system, scalar generalized Calogero-Moser system. The idea how to get spin generalized Calogero-Moser system is almost, well, absolutely the same as with usual Calogero-Moser system. So we take invariant parabolic ideal, we take the Weyl group module, and we tensor it with our factor module. So this tensor product is somewhat vector valued functions on the union of planes. And again, I said that on V, I want my rational Cherednik algebra to act trivial. And again, I want to do some explicit computation to see what can I get from this. So again, there are some technicalities. We need to act on, well, terms of functions. It's not so important, but we still can do it. So since we have a union of planes, we cannot, and my s's, they permute x's. So I can go through, I can act by s and move from one plane to another. So I need to take a direct sum of jones around points. And then this will be a rational Cherednik algebra-Moser. Now I want to take, again, invariance of this space. Then I will restrict the action of my Weyl-invariant polynomials in nablas, and I will compute the results. So I take invariance with respect to diagonal action of two Weyl groups, and this will be a module for Weyl-invariant polynomials in nablas. And the result is that the space on which I want to act is just a tensor product of jones at one point on my initial plane pi, tensored with invariance with respect to my parabolic subgroup in my module. And now I need to be a little bit careful about the module I take, because I can take a module where I have no invariance with respect to my parabolic subgroup. Well, my space will be zero. It means nothing. I will not compute anything in it. So I need to take big enough space with enough invariance with respect to parabolic subgroup. Then, as I said, Weyl-invariant polynomials in nablas act on my diagonal invariance. And the corresponding operator is written here. So it's Laplacian minus some, there is a derivative missing in the second term. Sorry about that. And there is a potential term almost the same as in the non-generalized version, again with the difference just being alpha hat in the denominator, but in the numerator I do not have alpha hats. So, oh yeah, and yeah, it should be y instead of x in the third sum. Okay. So again, it kind of looks like the difference is only in that I put hats on my roots in the denominators. So that's the general formula. I can go to the potential gauge to obtain my result, resultant operator, to see what the potential is. And the potential looks as follows. And it's almost what we expect from usual Calogero-Moser, something like c squared plus c pi, cp. Here it's almost like this, but I need to sum over all roots, which go to proportional roots after projection, which is kind of weird, but still this operator defines an integrable system. So C alpha hats, they are sum of all multiplicities of roots which go to the same projected root. And P alpha hat is quite a nasty expression of multiplicity function, P operators, constants, everything. Well, it's not so nice. I want to understand if I can write it more invariant. And actually, it turns out that yes, we can do that if we take a particularly nice representation V for my Weyl group module. So what do I have? So one of the simplest representations of Weyl group is a reflection representation. So let me take V as a reflection representation. But then I have quite a nice description of this P alpha hat. So if I say that V is a reflection representation, then this big thing, P alpha hat, firstly, it preserves the plane pi. It's good. But Moreover, it's really a reflection on the plane pi with respect to the projected root. Now I have the following picture. I have my plane pi. I project all my initial root system to plane pi. I obtain a collection of vectors, and I have reflections with respect to them. And for the case of reflection representations, this operator is generalized spin deformed Calogero-Moser operators considered previously by Chalykh, Goncharenko and Veselov. So, yeah, so just a few words about trigonometric case. So everything could be done in absolutely similar manner. Reducible representations are more or less the same. And we can do absolutely the same thing and we'll obtain the following operator with P alpha perhaps missing in the second sum. Here, the formula is not so nice. We have a sum over roots which go to proportional roots after projection with two hyperbolic cotangent function. Well, it's not so nice, but let's assume that after the projection, only proportional roots are alpha and 2 alpha, which is quite usual for us if we think about usual root systems. Then still, this formula is quite nice. It's relatively simple. And this expression c squared alpha plus 2 c alpha ct alpha, blah, blah, blah. So this is really the same constant as in BC type usual Calogero-Moser. So it is really quite nice, but only for reflection representation. We don't know how to write invariantly formulas for other representations. We do have them, but they are just big. We know that the operators commute, but we do not know how to think about them nicely. About these operators, we can write them just knowing the projected root system. So now we have this object, a projected root system, and we know that multiplicity functions must be very special for this operator to be integrable. Well, let me talk a little bit about examples. So for type A root system, we take a Dunkl diagram, and we know that multiplicity function should be 1 over constant number of subgraphs. So my connected subgraphs should all be of the same length. And that's it. I just take a number of connected A-type subgraphs, and that's it. And the resulting projected root system is almost type A root system, but deformed by K, which we have seen previously in the example. Now I will show you several examples coming from exceptional cases.
So would you go back to the previous
Yeah.
example? So you're marking certain nodes to indicate the subdiagram, but it seems
Yes.
like you're marking all nodes.
Now,
What does it mean that between the second and the third there's no red? There's no red.
yeah. Here I mark just two A2 subgraphs.
Yes, but they are neighboring. So what does it mean that you don't have the black, the connection between the second and the third node? Should you leave a node in between to indicate they're separated?
Oh yeah.
Right?
Yeah.
That's fine.
Yeah, thank you.
Fine. Okay.
Yeah. Correct. Yeah. So about this. Yeah. Yeah. So several examples coming from exceptional cases. So if we take F4 and this subgraph, well, we obtain something, well, quite weird. But I mean, of course, it's not a root system. And for example, if we take a particular root and take the orbit with respect to all reflections coming from this root, well, the usual situation is that the orbit will be dense. So it's not a root system, absolutely, but still it has some nice properties ensuring that we have some integrability. So here is an example for E8. Again, we have alphas and 2 alphas. Well, it's quite similar to well, it looks a little bit like a previous F4. Well, here is different. Again, we take E8, but we take different subgraph. And we obtain, well, a different projected root system.
You make choices of subgraphs so that you do get them. So you classify the cases for which you do get them.
Yes.
So you say this is not a root system.
Yes.
Can you classify some examples of subgraph choices where you do get them? Or is it just you never get the root system? Apart from the trivial choice.
I don't know. I think never, but I mean, I'm very sure that it's very exceptional. So I don't think that's kind of correct, like, question to. I mean, almost always is just something weird. Yeah. So for E7 and this D5 subgraph, we obtain something, well, quite simple, but still it's not a root system. But I mean, these pictures are quite nice. We can play this game, try to draw these two-dimensional projected root systems. We know that there is some integrability behind, but how to rephrase the properties just using this collection of vectors? At least I do not know a good way to do this. But yeah, so let me just say a few words that there is a classical story that for the usual trigonometric spin Calogero-Moser, we can write additional integrals of motion, not coming just from Cherednik algebras, but from Youngian. It's called Dirichlet functors. So it more or less says that if we have degenerate affine Hecke algebra, then we can, from a module of it, we can construct a representation of Youngian using Dunkl operators as evaluation parameters. And then we can take any maximal commutative subalgebra inside the Youngian. And the center of the Youngian will generate Weyl-invariant polynomials and Dunkl operators. So this very nice construction works in type A. I'm quite sure it works in other types, but I think with reflection equation, well, it's not so nice. But in type A, it's very simple. We can do all the calculations. Yeah. So then we can take beta subalgebra, we can take Van-Sapien subalgebra, whatever. We'll get a lot of additional integrals of motion, and this, of course, will work with our deformed generalized spin Calogero-Moser case. Just because we need a module for degenerate affine Hecke algebra, and we do have it. So yeah, so the summary of my talk is the following one. So we started with the polynomial representation of rational Cherednik algebra. We took an invariant parabolic ideal which exists for certain choices of subgraphs and multiplicity functions. We tensor it with the vector part, which is a Weyl group module. And then we compute integrals on the space of diagonal invariants. And then we see that for the case of reflection representation, reflection representation, we can write Calogero-Moser operators almost using only the information about the projected root systems. Yeah, so what we can do next, and what are nice questions about this? So we can try to generalize this to elliptic systems. Then we can consider full Daha and consider the case of Schneider model. We can try to study low-rank cases of projected root systems to understand what is so nice about them, what we can say about them. And also we can try to think about monodromy-free operators using results of Chalykh, Veselov, and Goncharenko. And again, we can try to understand for which choices of subgraphs, multiplicity functions, we do get monodromy-free operators, and for which we do not. Yeah. That's it. Yeah.
Question. Seems you a little more about the relation of Cherednik algebra and the relation with Daha. You said you can consider for Daha.
Yeah. So, well, the relation is, well, quite simple in some sense. So rational Cherednik algebra is, so you need to degenerate twice Daha to get rational Cherednik algebra. So in Daha you have Hecke relation, for example, for T's. In rational Cherednik algebra, you just have a Weyl.
Okay.
Yeah, and for x's and numbers, you kind of do something like exponentiation. So Daha operators are somewhat like exponents of x's and numbers in rational Cherednik in rational Cherednik algebra.
Okay. And why 1.3 operators are interesting? Like, what's the purpose of studying like 1.3 operators?
Well, well, it's if we think about differential operators, it's quite usual for the solutions to have
Right.
yeah, and monogamy free operators should be some very special case.
Yeah.
So this would be somehow a definition of very nice differential operator.
Okay.
And maybe there could be a description. Well, we could try to search for particular projected root system for which this is true, and maybe we can understand kind of a subset of very nice projected root systems about which we can say something.
Okay. My last question. Right?
Yeah.
How much do we know about the eigenfunctions of these operations?
Yeah. So
Yeah. You're some kind of polynomials.
yeah. So I can't say a lot about spin version, but about scalar version, I think there are some versions of deformed Jack polynomials.
Okay.
And also for McDonald's operators, there are also deformed McDonald's operators. They have been studied by, I think, Martin Kalmas and his co-authors. There are some scalar product formulas, integrals. So, yes.
But they'll have different norms, right? Different, they're like, is the norm the same or different? Depends on certain things.
I don't know. We can try to look at
Kind of symmetric numbers, but bisymmetric, where you have two subsets.
yes, but
So it can be just Jack, something.
yes, they are bisymmetric, but there is also some relation between x's and y's.
But you can't replace one with one,
Yes.
y by one.
I can't replace x and y. Yes, I can't. Yes.
Thank you.
What can you say about the centralizers of the deformed system?
So it means so is the question about spin version or about scalar version?
Both.
Yeah, so let's say we speak about scalar version, we act on polynomials in, let's say we are in type A, X and Y's, and you ask what operators do compute with them, right? I do not know the answer. It's a good question.
In the work of Big, Charles, and other guys you mentioned, they also, when they did constructing the Goncharenko and Veselov systems, they proved, but it's all part of them, that the centralizer is isomorphic to so-called algebra of quasi-invariant polynomial. Do you have some similar results here?
No, we haven't studied this. Yeah, but yeah, that's a nice question. Yeah, thank you.
Do there exist some kind of analogous with generalized Treacher function, like in variables?
Yes, I know about. Yes, yes. There is some analog, I haven't studied them, but I know that, for example, Martin Vrabec works on them. And I know that they try to study some particular low-rank case of this projected root system and analyze it using Baker-Heiser function. Yeah, so they exist in this sense. Yeah.
And also the last question in the case of two variables.
Yes.
As far as I remember, there was a recent work by Chalykh and Veselov where they aim to classify all potential, all integrable potential. How this paper fits this.
I haven't seen this paper. Was it like in 24, 23?
22.
Oh, 22.
Too old.
No. I do not know. I should look into it. I mean, I might ask Misha because I'm quite sure that he knows about this.
Sure.
Yeah.
Okay.